Yep. All right, so we're going to start here with chapter 2, which is about measurements. So in this chapter, we're going to talk about measurements, scientific notation, significant figures. We're also going to talk about conversions, dimensional analysis, which is, as we've been talking about, they do want you to have certain skills as you continue on to 1A and 1B, and dimensional analysis, which is how they really want you to solve problems as you go through chemistry. We'll talk about how to do that in this chapter as well. We'll finish up with this chapter on density. So let's get right into it here. So first off, really important when we do take measurements is the idea of units. And a measurement should really always have a number, sort of a numerical value, and it should always have units. Once again, if you write 100, you just go, hey, I have 100, really what does that mean? If you have 100 cupcakes, it's different than if you had, $100, or if you had 100, different things. So the unit is always really, really important. It gives everybody sort of a frame of reference for what the number means, what the value may represent. So always when we take measurements, you should always have a number to the proper number of significant figures, and you should always have the units associated with it. And you should always get in the habit of writing both of those things when you do take a measurement. I will say in lab, most of your lab papers, they kind of fill in the units for you on the data sheets. But when you get into the calculations part and other parts of the sort of lab and the post-lab questions, you want to make sure you always include units, both in your calculations, when you record measurements. They're really important. Now, when we talk about units, there's really two sort of widely used units. There's the English sort of units, their system of units, which we use, and then pretty much everybody else in the world uses the metric system. So the metric system is sort of a very big one. So you can imagine as the world sort of got smaller and people sort of interacted, done business with each other around the world, everybody using different units is actually not a great thing. It has led to some problems in the past. So in 1960, they got together in a conference of weights and measures. Sounds like fun. But they got together, and really what they came up with was sort of a standardized system of units, which is what is referred to as the SI system of units, or the international system of units. And really it is pretty much the metric system is really what it's based off of. So you'll hear a lot sometimes about SI units and stuff like this, and it's sort of the standardized system of units that we use here in chemistry. And that allows everybody to maybe be on the sort of same page in terms of units and what numbers represent. Now, there are certain types of units and different quantities that they represent. And for example, the mass is represented by the kilogram. And you should kind of know these sort of representative units here. Length is a meter. Time is seconds. Temperature, which you may not be familiar with too much, but you definitely will be by the time you take this chemistry class and other chemistry classes. The really sort of standardized unit of temperature is Kelvin. It's actually abbreviated with capital, as you see there. And I will say pretty much every formula in chemistry, probably 99% of them, if you have something to do with temperature, it's got to find its way to Kelvin. It's really the unit that we use a lot in chemistry. There's other units like amperage for voltage, also moles, as we'll talk about in some later chapters. But these are the main ones that we do come across a lot. The other really important thing is to really understand, what you represent. Are you talking about something that is a volume? When units. So take a look at some of the with length. As we talked about, a meter, 1 meter is 39.37 inches. Centimeters is a very common unit that we do come across a lot in chemistry. 1 centimeter is 0.01 meters. are 1 times 10 to the minus 2 meter. A decimeter, 0.1 of a meter, and a kilometer is 1,000 meters. So these two are probably ones you should know. We do again come across those guys a lot. Very common units of meters, centimeters, kilometers, and millimeters is another one that we do come across a lot or use a lot. There is 1,000 millimeters in a meter. So that's another one that we do see a lot. Thank you. This is a table from your book, and the metric system, if you're familiar with it or not, we often use prefixes to change the meaning of some of the numbers. Not really change the meaning, but make the numbers a little bit more manageable so we don't have really large numbers, maybe really small numbers. And oftentimes when we do look at prefixes such as what we see here, and as we talked about before, this is probably a table you should know. I will say definitely in here, kilo, centi, milli, we do come across a lot, but throughout chemistry, 1A and so forth, micro, nano, pretty much this entire table does come up a lot. Now, when we see this, there's really two sort of representations that we come across in terms of the meaning of each of these. In most tables, if you look at this or you memorize it, usually this is what you see here. And that's sort of the power of 10 scientific notation, meaning this is basically this guy, which is 10 to the 6th, is the same as 1 times 10 to the 6th in scientific notation. Now, I will say that probably for the most part, people pretty much screw this table up when they try to use these conversions. They always use them backwards. So when we look at this column specifically here, this represents how much there is in the base unit in one prefix unit. So what do I mean by that? I mean that if I have, for example, centi, which is right here, 10 to the minus 2, and 1 centimeter, there would be 10 to the minus 2 meters. So it is a very common that people always want to do 10 to the minus 2 centimeters is 1 meter, which is absolutely wrong. So people always sort of reverse these things incorrectly. The base unit here is meters, right? So meters is the base unit on both of these. So again, if you had 1 kilometer, we would find kilo, which is here. That is 10 to the 3, 10 to the 3 meters. And again, that is the proper way to use those numbers, and very common. People always. It doesn't, it works the same. So if I had 1 centiliter, which is a volume, that would be 10 to the minus 2 liters. If I had 1 kiloliter, which is a volume, that would be 10 to the 3 liters. So it does work the same regardless of what the base unit is. But that is always, again, what you're seeing there. Any questions on that? Now, sometimes people will use a bigger number instead of sort of the exponent number. So for example, there are 100 centimeters in 1 meter, and you get that by taking 1 centimeter equals 10 to the minus 2 meters and divided by 10 to the minus 2 to both sides. And you end up with that. Some people use sort of the bigger numbers in those conversions, which is perfectly fine. I would say probably in most books and tables, you'll see sort of the 10 to the 6, 10 to the minus 3 version of it. So in that version, that is how much there is in the base unit and one of the prefix units. So once again, if we had 1 nanometer, that would be 10 to the minus 9 meters. So you want to make sure, honestly, you should probably know these. And definitely, like I said in here, probably kilos, milli are the three popular ones we'll come across a lot in here. As you continue on to 1A and stuff like that, you'll see a lot of micro, nano. Yeah, but probably for here, you should probably know what's on here. That's a lot, kilo, centi, milli, you know, a lot of the times. Any questions on that there? Here's the difference between English. We use inches here. So 1 inch is 2.54 centimeters. And that's everybody's favorite conversion that you need to know. 1 inch is 2.54 centimeters. And that's an exact conversion. So that definitely is something that you do need to know. I don't know how often you'll use it, but occasionally you'll use it, but you do need to know that. By the way, this is a ruler, right? These are inches. The big numbers here are centimeters. What are the small numbers? Yeah, the small little dashes right on the bottom there are millimeters, right? And there are 10 millimeters in a centimeter, right? So it's a good thing to know. A little bit about volume. The amount of three-dimensional space that's basically occupied by a substance. Volume is basically length cubed. The SI unit is meters cubed. So 1 decimeter cubed is equal to a liter. I would say on volume, these two for sure are ones A you should know, and B we use a lot. So 1 cubic centimeter is equal to a milliliter. It is basically a 1-to-1 conversion. So if you have to convert between a cubic centimeter and a milliliter, basically just change the unit. The number stays the same. And 100% of the time, we use a lot. 1 liter is 1,000 milliliters. Pretty much most volumes that we use in lab are even really in sort of problems that we come across. A lot of times the volume is given in milliliters. So that kind of liters to milliliters conversion is used a lot. And sort of, I would say probably most of the time, you would probably be given liters and have to convert it to milliliters. So that's something that you do a lot in chemistry. Another thing here, you may be saying cubic centimeters. You know, 1 cubic centimeter is also equal to 1 cc, which is a cubic centimeter as well. You sometimes hear that in like medical shows, right? Cubic by 10, right? That's basically the same thing as a milliliter. So it is important, as I talked about before, sort of the recognition of, you know, what do these units represent? So when we look at just a measurement like a centimeter by itself, that is definitely a measurement of length. But when we take basically 3 length measurements together, especially like in a cube or something like that, if we take like the length times the width times the height or the thickness, and if you measure each of these things in centimeters, you get centimeters times centimeters times centimeters, which gives us our cubic centimeters, which is a volume. So basically, if you take any sort of length measurement cubit, will give you the volume of the object. That is something that we do a lot, especially in these opening chapters. When we start talking about density, is a very common way to figure out the volume of a solid. You'll do it today in lab. You'll take like a solid square and basically take those 3 measurements and be able to figure out the volume of your little wooden block. Any questions on that there? Now, mass is another important unit. I would say definitely kilograms, grams, and milligrams. All 3 of these are very, very common units that we come across for mass. Mass is really the quantity of matter that's present in an object. Matter is pretty much anything that has mass and occupies space, which is pretty much everything. So we have 3 states of matter that we're commonly probably familiar with: solid, liquid, and gas, right? Those are the 3 states of matter. We use apparatus like this, like you will use today in lab as well. This is what is referred to as a balance. It's an analytical balance, electrical balance. Whenever you take any type of reading of anything that is digital, all the numbers are important. So you should always record all the numbers. You should never lop off any numbers out of a digital display. They're usually always important. Definitely these couple of conversions we do use a lot. Grams is a kilogram. And also 1,000 is another one that we do see a lot. Now, there is a difference between sort of two words that are sometimes commonly used, maybe interchangeable, and that is weight and mass. Now, weight refers to basically the effect that gravity has on it. So weight is dependent on gravity, while mass is sort of you weigh yourself weight different. Science put to the balance to weigh something. We do refer to it as the mass of the object rather than the weight, and that's the way that you should refer to of the object when you do that, which again is sort of independent of the force of gravity. Now, temperature scales are important. There's really three sort of major temperature scales that we see here. And those three scales are degrees Fahrenheit, and abbreviated like that. Water boils at 212 degrees Fahrenheit and freezes at 32 degrees Fahrenheit. That's obviously the temperature scale that we use, obviously, when we take our temperature and things of that nature. There's also the Celsius scale, degrees Celsius. Water boils at 100 degrees Celsius and freezes at 0 degrees Celsius. Those are two numbers that you should know. It is sort of thought of as you continue on in chemistry as sort of common knowledge for you that water will boil at 100 degrees Celsius and it will freeze at 0 degrees Celsius. So it's definitely two numbers that you do want to know. The third temperature scale used to be called the absolute temperature scale. It was later renamed for, a guy named Lord Kelvin, and it's now called the Kelvin temperature scale. And for Kelvin, it is a little bit different than the other two in the sense that it is just K for Kelvin. There is no degree written with it. So you say something like 273 Kelvin. You do not say 273 degrees Kelvin. And on the Kelvin temperature, water boils at 373 Kelvin and 273 Kelvin, it will freeze. I will say added these three sort of temperature scales pretty much for the rest of your chemistry journey, probably outside of chapter 2. It's going to be degrees Celsius and Kelvin with, like I said earlier, pretty much 99% of formulas require the temperature to become Kelvin. So most of the time you will find yourself be given the temperature in Celsius. Most of our thermometers will give Celsius, and you will most oftentimes have to convert it into in chemistry here, and that's a very, very common conversion. I would say a lot less common, but sometimes occurs would be going the opposite way, Kelvin back to Celsius. Probably outside of chapter 2, you're not going to see very much of Fahrenheit at all. That usually doesn't pop up on but definitely Celsius is a very common unit, and that conversion from Celsius to Kelvin, definitely very, very common. So here's sort of the different temperature scales and where they freeze and boil. And it is actually the difference between freezing and boiling, which basically gives us our conversions to between the two. Again, there's about 180 degrees difference on the Fahrenheit scale. On the Celsius and Kelvin, you're about 100 degree or units difference between them. So it is important to know those conversions. So let's talk about how to do these. And once again, they will not be provided for you. So you really do. And as I mentioned before, probably outside of chapter 2, that is definitely the one you should 100% commit to your memory because you will use it the most. So if we wanted to convert Celsius to Kelvin, we will add 273 to the temperature in Celsius. The correct proper number is 273.15. I can't remember the last time I actually seen somebody use the 0.15 part of it. If you like the 0.15, you can use it, but I will say probably most people, if not all people, will just simply use the 273. But if you want to keep it in, you can. In most cases, it'll probably just get rounded off anyway. So that's why most people kind of just do 273 rather than 273.15. Again, this is probably the most conversion you're going to be doing. Occasionally, you will go the other way, which means if we subtract the 273 to the other side, temperature in Celsius would be our temperature in Kelvin minus 273. So if you need to go the opposite way, you will subtract 273 from it. Probably very much not used all that much, but you do still need to know them. The temperature in Fahrenheit is equal to 1.8 times temperature in Celsius plus a 32. And want temperature in Celsius and you have Fahrenheit, you're going to subtract the 32 to the other side and divide the 1.8, and that gives you the guy on the bottom there. Temperature in Fahrenheit minus 32 divided by 1.8. Now 1.8 is the same as maybe you learned when you're younger as well, maybe 9/5. If you take 9/5, you get 1.8. So that's the same conversion if you want to use more of a fraction version of it. If you have Fahrenheit and you got to go from Fahrenheit to Celsius, Celsius to Kelvin, and vice versa, you got to kind of go all the way across if you want to go anywhere. So you do need to know these. Any question on that? Now, speaking of giving the answer to the correct number of digits, there is really a special sort of rule that most people follow, and we will follow in this class. When you are doing temperature conversions, if the only thing you're doing is strictly taking a value from one temperature scale to the next, and you're doing nothing other than just converting the temperature scale, your answer should look like the original number. And what I mean by that is if the original temperature value was a whole number, when you do the conversion, you should convert it to a whole number. If the original temperature value went to the first decimal place, when you convert it, you should take it to 1 decimal place. If it went to 2 decimal places, you should take it to 2. The reason for that is that really doesn't follow strict significant figure rules, but the reason for that is really the conversions that we use here. For example, 1.80 is here. Some people use 1.8. Some people use the fraction. So there's a lot of variations that you could get in terms of significant figures. So the general rule is whatever the original number looked like, the converted number should be the same. So if you had, 1 decimal place to Fahrenheit and you converted it to Celsius, it also should go to 1 decimal place. If you had a whole number for degrees Celsius and you converted it to Kelvin, you should have a whole number for Kelvin. Any questions on that? All right, let's try some here. Let's take a couple minutes. We're going to convert Celsius to Kelvin, Celsius to Fahrenheit, and Fahrenheit to Celsius. Take a moment or two, grab a calculator, make sure we all end up in the same answer. Okay, let's take a look and see how you're doing. So on the first one here, we're going to go from basically Celsius to Kelvin. So we want our formula there. So remember, our temperature in Kelvin equals 273 plus our temperature in Celsius. That would give us 273 plus 28.5. And if you punch that into your calculator, looks like 301.5 Kelvin. A reminder, a couple of things. Again, we do not use the degree sign there. So it's just Kelvin. Again, our original value here went to 1 decimal place. So when we did the conversion, we do keep it here to 1 decimal place. Again, making the answer look like the original value. Any questions on that one there? Coming here to Celsius, we want to convert Celsius to Fahrenheit. So our formula is the temperature in Fahrenheit equals 1.8 to temperature in Celsius plus a 32. So we take 1.8, we times it by 41, and we add 32 to it. Gives us 1.8 times 41 plus a 32. On our calculator, we do get 105.8 degrees Fahrenheit. In this case, I should take that to what number? I should take it to 106. We look at our original number here, which was a whole number. We would want to round this to 106 degrees Fahrenheit. We would round up because this number is above 5. Yeah. Any questions on that one? Lastly, here we are looking at Fahrenheit to Celsius. So that's going to be our temperature in Fahrenheit equal temperature in Celsius there. We want to do the opposite there. Try that again. Temperature in Celsius is what we're looking for. So our temperature in Fahrenheit minus 32 divided by 1.8. Temperature in Fahrenheit was 160 minus 32 divided by 1.8. So 160 minus 32 hit equals divided by 1.8 hit equals. Gets you 71.1111 degrees Celsius. I should take this one too. Should take it to 71. Once again, our original value here was a whole number, so we will take it to 71 degrees Celsius. Any question on any of those conversions there? So once again, original number, make the converted number look the same. That again is specific for just temperature to temperature conversions. That's all you're doing is just converting the unit. And as I mentioned before, definitely Celsius to Kelvin. You need to know them all, but definitely commit to memory the Celsius to Kelvin conversion for sure. All right, so as I mentioned earlier, it really is important to understand when you see a unit or when you say a unit, what it means or what it represents. I can't tell you how many and say, you know, my volume reading was 35 grams. Grams is obviously a mass, not a volume, right? Or, you know, my mass reading was 200 milliliters. So it's really important to understand that when you do state a unit, you understand what it's representing. So for example, here, if we look at the unit, we have Kelvin. That obviously is a temperature. We have liters, which is a unit of volume. We have meters, which is a unit of length. And lastly, we have kilograms, which is a unit of mass. So it's really important to understand those things. And, you know, it happens a lot with people. So make sure you understand that, you know, I have 50 kilograms. You understand that you're talking about a mass, not a volume or a length or temperature or anything weird like that. All right. Also a good time to talk about a couple of different types of evaluations that we make when we are doing things. There's qualitative, and qualitative basically are our general observations about something. You know, it's purple dots, it's on fire, whatever it may be, right? So qualitative sort of observations are just that. They're really observations that don't involve any type of measurement. So you didn't do anything other than just kind of observe what's going on. Those are qualitative. When you take 1B, you do a bunch of experiments that are known as qualitative analysis, which has absolutely really no measurements, no calculations other than you mix these two things together and a thing turned purple, which means you have this ion basically. So it's all just, you know, observations of what occurs. What we do a lot in sort of general chemistry in this class and so forth, and in lab, we do a lot of quantitative types of observations. And quantitative observations really are measurements. And they are guys that are basically achieved through some type of measurement. There's a number, there's a unit, there's some type of actual piece of equipment that you use to make a measurement, and those are quantitative. In lab, as you go through chemistry classes, it's good to always record both types here. In addition to taking the measurements, how much you got of this or how much volume that you may have, it's also really important to take qualitative observations of what's going on. Like I said, you mix these two solutions together, or some type of solid or precipitate formed, it was yellow. These are a lot of things that sometimes can really help you understand what's going on. But the quantitative part of it should always involve some type of measurement, some type of number, unit value associated with it. Any question on the difference between the two? So let's talk a little bit about scientific notation, just to make sure everybody's on the same page. Clearly in chemistry and a lot of sciences, we do come across a lot of really large numbers, a lot of really small numbers like we see here, like Avogadro's number there, 2, and a bunch of zeros, or the mass of a hydrogen atom, which is a bunch of zeros there. And if you were to sort of keep the numbers like that, there's probably a pretty good chance you're going to out on the zero. When we're in science, especially in chemistry, we oftentimes will use scientific notation to large numbers, really small numbers. There is a formula that we use for scientific notation. When you write something in proper scientific notation, it should have this sort of setup: n times 10 to the n. This n is a number between 1 and 10. So it can't be 10 or higher. It can't be less than 1. It's got to be a number between 1 and 10. And depending on how many places you need to move the decimal point to get to a number between 1 and 10, this guy up here will either be positive or negative, depending really on how many places you got to move to get there. So for example, if we had 5, 2, 6, 8, and we wanted to turn it into scientific notation, we would assume the decimal point would be there. If I moved it just one place, that's 526. That is not between 1 and 10. If I move it 2 places, that's 52.68, still not between 1 and 10. I need to go one more place, and that is now 5.2, which is a number between 1 and 10. And this would be 5.268 times 10 to the 3. 3 because I moved it 3 places. I moved it 3 places to the left. It's a positive exponent. Easy way to remember it is large numbers have positive exponents. So 5,200, whatever that is a large number. It has a positive exponent. If you have a smaller number, like 0.0123, if I go one place, that's 0.1. That is not a number between 1 and 10. I need to go one more place. That is 1.2. That is a number between 1 and 10. And this would be 1.23 times 10 to the minus 2. 2 because I moved it 2 places. Negative because it is a small number and I moved it to the right. So small numbers have a negative exponent. Large numbers have a positive exponent. Any questions on that? Do you have to give the answer in scientific notation? The answer is no, you don't really have to. I personally don't care. As long as the answer is given to proper number of significant figures, which we'll talk about later. You might run across some teachers that I know there's like everything needs to be in scientific notation, but you really don't have to for us in here, unless obviously the question says put it in scientific notation. But other than that, if you want to, you can. If you don't want to, you don't have to. But you do have to give it to the right number of digits. With that being said, as we'll talk about a little bit later on, there may be only one way to get a number to the right number of digits, which is to use scientific notation. Is the idea that when you do write it in scientific notation, all the numbers before the times 10 part are significant. They're basically significant figures, which means this number would have 3 significant figures. This number here would have 4 significant figures. So because you can, with scientific notation, sort of determine how many numbers you put there, sometimes that's the only way you can kind of get the right number of significant figures. We'll talk a little bit more about that a little bit later on. In addition to be able to write numbers in scientific notation, I think just as important, or maybe more important, is to be able to actually put it in your calculator correctly, because that's most of the time how you're going to use it. And I am very much aware that most people don't actually know how to do that. So let's talk a little bit here about how to actually put it into your calculator correctly so that you will hopefully get the right answer. On all scientific calculators, there actually should be an exponent button. It is a button that either says EE. It is a button that typically will say EXP. And if you have sort of the newer-ish calculators, you may actually even have a times 10 to the end button. And if you do, I'm sorry, but we'll talk about you in just a second. If you have the other two buttons there, which are very common as well, those are actually your exponent button. So you shouldn't be using the log button to put things in scientific notation, using like the caret or anything like that, the inverse log, because that is clearly incorrect. So for example, if I wanted to put into my calculator 4.75 times 10 to the minus 7, the way I would actually put that into my calculator is as follows. 4.75, I would then hit my exponent button. I'm not going to hit the multiplication button, not going to hit anything else, just my exponent button. And usually your calculator would probably display 4.75 in an E, or 4.75 and maybe a couple of zeros. Maybe it actually says really small, like times 10, and puts a couple of zeros up, something like that. When you actually hit that exponent button, the EE button, the EXP button, it represents this part of the number. So when you hit this guy, it represents that part of the number, the times 10 part, which means you do not need to put the multiplication button. You don't need to put anything weird like the inverse log button. All you have left now to put in there is actually the -7, which brings us to another important button on your calculator, which is the negative button. Most calculators have a negative button that looks either like this or it looks like this. It is not the subtract button. So you got to hit your negative button at this point. That's going to put a negative. That's going to put a negative. And then at this point, you just put 7, put 7. This thing will then change to 7. And that is the proper way to punch into your calculator a number that is written in scientific notation. If you do not do that and you do all kinds of weird things like the multiplication button, the inverse log button, what you will find is your answer in the front part will look good, but the exponent part will be off. And that's usually because you're not putting it in correctly. Now, for those people that have actually this button, and usually if you have this button, kind of like a two-tone calculator, usually it's got like a color on the outside and like white. You also usually have like a little dial on it as well, a little wheel type of action. So if you have that, you just got to do a couple of extra things on yours. You actually need to put parentheses around every number that's in scientific notation. If you wanted to actually do the math right, you need to put a parentheses and then go 4.75, then hit your exponent button. On your calculator, it looks like this, 4.75, it'll say times 10. You'll have a little blinking box up on top. At that point, you would then hit your negative button and 7. And when you do that, you will then have 4.75 times 10 to the -7. And now you'll have a small little blinking box up on top. Because that blinking box up on top, you actually need to go to your wheel and hit that usually. And what that will do is bring your little blinker down, and now you can close the parentheses. Then you'll have something that looks like that. If you don't do that, you just close the parentheses, you'll end up with something like this, with the little parentheses up on top, and you usually will get an error. So you got to kind of bring that thing down by using this. So if you have that button, you got to kind of do a couple extra things, but pretty much every number is in scientific notation. You need to put parentheses around it. to tell your stupidly programmed calculator how to do the math correctly. Otherwise, it will do some really bad math. So if you're not sure how to do it, you should come see me. I'll be happy to show you where your exponent button is and how to properly use it. But let's try a couple here to make sure. So let's do 3.25 times 10 to the minus 3. Let's divide it by 1.2 times 10 to the 23. And then let's do 4.35 times 10 to the minus 4 times 1.6 times 10 to the 19. All right, punch those in correctly using your exponent button. I'll do it as well since I just made it up. We'll hopefully both end up in the same spots. 3.25, I would hit my exponent button. I would hit my negative button and 3, then hit my divide button, 1.2, and do an exponent button on this guy. It's a positive exponent, so I could just put 23, then hit equals. And if I do all that good stuff right there, we get some number. Let's see. Looks like 2.7 to the minus 26. I rounded a little bit here, obviously 2.708333 times 10 to the minus 26. By the way, that's a reminder that your calculator will give you maybe something like this. Then maybe really small in the end of it, it will say minus 26. So you don't want to forget that part when you give the answer on your screen. Yeah. It actually will be 2.7 in this case. We'll talk about, we haven't talked about it yet, but basically based on significant figures, the answer should be actually 2.7 in this case. Now that is the proper way to give the answer. You should not give the answer as 2.7 E minus 26. That is not scientific notation, yes. Although E is used to represent the times 10 part. When you are writing the answer, you do need to write the times 10 part. If you have this number correct, but this number is off, is probably the way you're punching into your calculator. Yeah. So take a look at the bottom one there. Once again, we'll do a 4.35. We're going to hit our exponent button. Going to hit our negative because it's -4 and hit 4. Going to hit the times and 1.6 exponent button. And again, this is positive. So we'll do just 19 and 4.35 -4 times 1.6 exponent 19 gives us we'll call it on the calculator, gives us 6.96 times 10 to the, I guess it's 15 if I'm not mistaken. Yep. To the 15. Really it would round in this case to 7.0 times 10 to the 15, but more importantly, you know, that is what you will see on your calculator. Any questions on how to punch it into your calculator? Really important to be able to do that. Lots of numbers across you in scientific notation. A couple things about your calculator, right? It does not always give you the answer in scientific notation unless you have a program to do so. And it doesn't always give you the right number of significant figures, right? So what you see on the calculator is not always the right number of digits to put as your answer. And we'll talk about obviously how to know what the right digits are. Any questions on that? Again, if you're still struggling with your exponent button, just come see me. I'll be happy to show you on your calculator. If you have that other button, the times 10 to the end, you would do the exact same way, just put the parentheses on both sides of the numbers. All right. So let's take a look at some of these guys, turning them into scientific notation. Here, 568, we need to go 1 and 2 places to get to 5.68. 762 times 10 to the 2. In this case, we need to move decimal place 1, 2, 3, 4, 5, and 6 places to get to a number between 1 and 10. No decimal written, but assumed here. So we would go 1, 2, 3, 4 places to get there. And lastly, just 1 place here to get a number between 1 and 10. Once again, our larger numbers, positive exponents. smaller numbers below 1, negative exponents. So again, just keep that in mind. So you do need to be able to write numbers in scientific notation. You need to be able to take scientific notation and convert it back to a decimal. And you need to be able to, obviously, most importantly, be able to punch it into your calculator and use it in calculations. Any questions on any scientific notation stuff? I'm going to skip that one, I think. So the next thing we're going to talk about is really about measurements. And when we take measurements, no matter what type of measurement that you take, there's always some degree of uncertainty that there is in any measurement that you make. The degree of uncertainty will be based on really the piece of equipment that you're using as to how bad or good of a measurement that you can take. So for example, let's take an example of a ruler here. Sketch one up here. So we'll go. To do a little, we'll call these centimeters here. So let's say we have here and we wanted to measure like an arrow or something. So we'll draw an arrow here. We'll go about there. Okay, so really when you take a measurement, there's two things that you want to look at. You really want to look at the scale and you want to figure out two things. You want to figure out, what does the largest markings on the scale sort of represent? In this case, the largest markings are really the big numbers that are written. So our largest markings here represents 1 centimeter, right? The other thing that you want to look at is between the largest markings, or between two largest markings, what does each of the smaller sort of markings represent? So we want to really count up how many smaller markings we have between the two big numbers, which in this case is 1 and 2. Now, when we do count, this is the way we count, which may be a little unusual for you. We actually count at the very first small marking past the number, basically. So that is our 1. We have 2, we have 3, we have 4, we have 5, we have 6, we have 7, we have 8, we have 9, and we have 10. So we basically have 10 markings between the largest marking. So in this particular case, because we have 10 markings, each of the smallest markings represents how much? 1 divided by 10 is 0.1 centimeters. Yeah. So each of the smallest markings represents 0.1 centimeters. By the way, I got that by 1 divided by 10 small markings. We'll get you there. That means that this number right here would be 1.1. This guy would be 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9, and 2. Everybody good so far? Okay. So whenever you take a measurement, there should be some numbers that, no matter who takes a peek at it, who looks at it, everybody should pretty much agree. So in this particular case, if we look at it, everybody should agree that it is at least 1.3. It is definitely not 1.4, but you definitely should agree it's 1.3. And you would want to record that. And when we record the 1.3, these are what are sometimes referred to as all of our certain numbers. Again, there really should be no disagreement there on those numbers. The disagreements now comes into play because when I look at that arrow, it's not exactly 1.3, it's not really 1.4, it's somewhere in the middle, right? In between those two. I may look at it and go, well, I don't really think it's exactly middle. I think maybe it's just a hair short of middle. So I may record it as 4 centimeters. This number is what is referred to as the first uncertain number, which is sometimes also referred to as the estimated digit. When you take a reading like this, you should always record in any measurement all of the certain number plus the very first uncertain number. That is important because that is what is known as significant figures. So when you record all of the certain numbers in a measurement, which you should do, and the first uncertain number, which is the estimated digit, that is what is meant, and that is how many significant figures it would have, which means this number here would have how many significant figures? This number here should have 3 significant figures, right? Now, when you look at that, it's assumed F4 is the uncertain number or estimated digit. Somebody else may look at it and go, well, I think it's like halfway there. So it's like a 5, or maybe it's a little less, like a 3. Usually it's plus or minus 1 of that last digit is sort of the error range within it. When you use a piece of like this, you can figure out the degree of uncertainty in that equipment. And you can figure out the degree of uncertainty by taking the smallest markings and dividing by 2. So in this case, the smallest marking was 0.1. Divided by 2 gives us 0.05 centimeters. So sometimes people will record this as 1.34 centimeters plus or minus 0.05 centimeters. This uncertainty takes us to how many decimal places? 2 in this case, and our reading went to 2 decimal places. So in general, if you take the uncertainty of an equipment, just take the smallest markings and divide it by 2, it will tell you how far you should take the reading to. So in this case, we should take it to 2 decimal places. To be a 5, but that's how far you can take it, is basically 2 decimal places. Question on that. Now, it does change depending on the piece of equipment that you're using. Let's say we had something that was set up like this. All these milliliters. There we go. It's artsy. How come I failed art 9 times? Okay. So this is a wonderfully drawn graduated cylinder. You'll recognize it when you open your drawer today. But this is a graduated cylinder. And whenever we sort of take a reading of a liquid in a glass container, there's usually a curvature of the liquid. And you usually will dramatically drawn see the liquid curve like so. This is what is known as the meniscus. And you always read from the very badly drawn bottom of the meniscus. The reason that is what is happening is when the liquid, like water, for example, goes into a graduated cylinder, the water is more attracted to the glass than the water itself. So what happens is the liquid on the side starts to rise up the glass. So what you have happening here, and we'll talk about in a later chapter, is the ends are rising up against the glass. But the actual volume, if that wasn't happening, is actually right there at the bottom. And most things will do this type of meniscus. There is actually a few things that will actually do a meniscus that goes the opposite way. Mercury is an example of that. It will actually read at the top. But in most cases, you want to read from the bottom of the meniscus. So if we put some liquid into here, we'll do lucky blue. We'll go right about there. Now, when I look at this, my large number on this scale is how much? What's the difference between those 2 large numbers? That is 10 milliliters. When I count the lines between those 2, starting here, that is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 markings. So I have 10 smaller markings between the big guys. That means each of the small one is how much? Yeah, 10 divided by 10 is 1 milliliters, each of the smallest markings. If I want to know my uncertainty in this piece of equipment, I could take my smallest marking and divide by 2, which would give me 0.5 milliliters, right? Which means really when I'm done reading this, that is where I should end up. So let's see how we get there. So this is 11. This is 12, that is 13, that is 14, 15, 16, and so forth. Now, if we take the meniscus here, ish, it is at least how much? It is at least 13. That is my certain numbers, right? Once again, it's not exactly 13, it's not exactly 14. So that is where the estimate's going to come into play. And maybe I feel it is halfway there and I put a 5 milliliters. And this would mean that this is my first uncertain number. And how many significant figures would this have? It would have 3 sig figs, right? Now, if I wanted to include my uncertainty here, we see my uncertainty goes to 1 decimal place. My answer went to 1 decimal place. So again, that will tell you how far you should take the reading. I could include that in if you wanted to. You don't necessarily have to do that for me in lecture, but in the lab, he may want you to do it. And you could do something like that. Yeah. Now, any questions? Yeah. Again, it does have to be. If the, for example, if the meniscus was, let's just say we had a different one in there. Let's say like the meniscus was like here, right? You probably want to go 0.5 at the end, right? You probably would go closer to like 0.9 or 0.8 or something like that. So you could use it. It doesn't necessarily have to be sort of 5. If it is near the middle between the two, most people will go with 5, but you can use any number you want. Any question on that? Yeah. Yeah, so we'll talk about that. It's a very good question. So let's talk about that right now. So typically speaking, you typically could go one more place to the right of the smallest marking. So in this particular case, the smallest marking was 1 milliliter. We're able to take our answer to one more place to the right. Here, the smallest marking was 0.1. We're able to go one more place to the right. And that typically is the case. It's not always the case. We'll talk about that in just a second. But since you asked that question, let's actually look at that question, which is a good question. Let's get rid of this. Let's get rid of this and stuff. All right. So let's say that we did have the exact same sort of setup here. But let's say now that our arrow was like dead on that number is what your question is, right? So we do have a couple of things that we could record. We could record 1.3 centimeters. We could record 1.30 centimeters. Could record 1.3000 centimeters. Is there an actual difference between these numbers? Are they all really the same because it all says 1.3? I'm assuming there's a difference between those numbers. So let's take a look at 2 of them. We'll get rid of the last one. Too many zeros. Making extra zeros doesn't always make it right. Yes. So if we take a look at the first value that we wrote, which is 1.3 centimeters, how many significant figures would this guy have? Would actually have 2 significant figures, right? Which means the uncertain number would be which number? It would be the 3, right? The last significant figure. So really what we're saying in this case is, I think it's 1.3, but it could be like 1.4 centimeters. It could be as low as like 1.2 centimeters. And when we look at this guy, is it anywhere near those two? It's not near 1.2, it's not near 1.4. That's a pretty big room of error, right? If we recorded 1.30 centimeters, how many significant figures would it have? It would have 3, yes, because we would be recording all the certain numbers plus the first uncertain number, and this guy would have 3 significant figures. Which one would be the uncertain number in this case? It would be the 0. And basically what that means when we record that is, it is 1.30, I think, but maybe it's 1.31, maybe it's 1.29, which if you look at this, that is really what you're seeing on that scale. So because you do have the ability to take the reading in this scale to an extra place, and if you feel it's like dead on, you do have to record it as a 0. Because basically when you get rid of that 0, you pretty much made your measurement crappy. Yeah, you made a really bad measurement, as there's a big difference in error between these two versus these two. So this would be the correct way to record that. Question on that? Yeah, really, even though, so there's a little bit of difference in terms of the uncertainty in the equipment, or sometimes referred to as the tolerance of the equipment. And that really is just kind of telling you how far you can take the reading. Most people assume when you lay down a reading like 1.30, that last significant figure, which in this case would be the 0, is kind of like plus or minus 1 is usually kind of where the, the difference is. But you have that sort of tolerance of the equipment that you can kind of take it that far out. So it doesn't necessarily have to have a variation between those. It could go as high or low depending on how good or bad you took the reading. But most people would consider kind of plus or minus 1 of that last number, but you could have that sort of plus or minus 5 span. Other questions? All right, so now let's take a look at one other thing here. Let's say we had something like this, and that's why it's always important to take a look at your scaling. Let's say we had 10. 20. Again, we had a nicely badly drawn graduated cylinder here. Put that as a 10. So we'll put some liquid right about there. Now, in this particular case, the large numbers that we have on the scale is how much? The difference between these two is 10 milliliters. We now have, in this case, in terms of the smaller markings between them, 1 marking, 2 markings, 3 markings, 4 markings, and 5 markings. So that means each of the markings in this case represents how much? 10 divided by 5 is 2 milliliters, right? So that means that this actually is 12, 14, 16, 18. So when I take my guy right about there-ish, what is between 12 and 14 in this case? It is, the number between 12 and 14 is 13. The best you could do on this scale would be 13 milliliters, which would have how many significant figures? Have 2 sig figs. The uncertain number in this case would be the 3. Yeah. We know that also by taking our tolerance here, right? Or our uncertainty by taking our smallest markings and dividing by 2, and we end up with 1 milliliter, which is what we took the reading to. So this would be something like 13 milliliters plus or minus 1 milliliter in terms of the difference here. The reason we can't say 13.2, 13.5, that is because in between 12 and 14 on this particular scale, there's no way to know exactly where 12 ends, 13 starts, 13 ends, right? There's not enough room there to figure that out. So the best we could do is go to the whole number. Questions? Okay. We will stop there for today.